Right, we're going to take a first look here at a way to get a value for the delta E for a chemical reaction. Right, the way we're going to do this first is to think about what are known as bond energies. These are pieces of information we can look up in tables for various types of chemical bonds. Right. We spent some time talking about bonding, and I've often commented the last few classes that we can measure the strength or the length of chemical bonds, right, by looking at how molecules rotate, by looking at, say, the wavelength of light that it might take to break a bond and pop an atom off of a molecule. We can measure these things, okay? When I say the strength of a chemical bond, I'm talking about how much energy does it cost to break that bond and actually tear the atom free. People have measured these for a lot of different molecules, and it turns out if you measure the energy of, for example, a carbon to hydrogen bond, that value for that energy, the amount of energy it costs to break the bond, is about the same for a really lot of molecules, okay? There are millions of different molecules, literally, that have carbon to hydrogen bonds in them, and the carbon-hydrogen bond energy is actually pretty close to the same across all those molecules. What that tells us is that the bonds are in a general sense sort of localized, right? Meaning that the energy, the strength of that carbon to hydrogen bond doesn't care that much about what's happening on the rest of the molecule, right? And so this is actually handy for figuring out reaction energies. This is a piece of a table of bond energies, okay? And if you searched online for a list of bond energies, you'd find a larger list of values probably. They're in kilojoules per mole, okay? Per mole, meaning this is the amount of energy it would cost if I wanted to break the bonds in an entire mole of molecules. So the first entry up top there says hydrogen. So that says take a mole of H2 molecules. That's the only molecule that has an HH bond in it, right? If I wanted to tear them all in half, so I had just H atoms instead of H2 molecules, then I would need to supply 432 kilojoules of energy to do that. If I wanted to convert that to how much energy to break one molecule in half, I could convert the kilojoules to joules if I wanted to, and then I would divide by Avogadro's number, right? Because that's still what a mole is Avogadro's number of things. If you look at this list, you'll see a few things. Up on top, where it says those are diatomic molecules, meaning those are real molecules that you can measure for, like in H2's case, right? That's the only molecule that has that bond in it. All right. So those are more accurately measured because they're all for just one molecule. Below that, we've got average values. Okay, these are averages because where it says, if I look at this one, carbon-carbon, right, that says measure the carbon-to-carbon bond energy in a whole bunch of different molecules, and they average to about 345 kilojoules per mole. Go across the row there, and I go from single bond to double bond to triple bond, and as I do that, the bonds get stronger, right? That means the bond energy goes up. It would cost more energy to break apart the double bond than the single bond. The triple bond more so than the double bond, right? If I look at this set here, these are all single bonds of various elements to carbon, and you can tell they all have different bond energies. They're all in the same general order of magnitude, but they've got different values there, right? So this says just some bonds are stronger than others. That shouldn't be really surprising to us, all right? These are things you're not supposed to memorize any of these numbers or just know any of these numbers. I don't know these numbers, okay? There are things that if you needed them for a problem, the information should be somewhere handy and nearby. So what can we do with these? Why am I even mentioning this, this tabulated data? The reason is we can use them to calculate delta E, or an estimate of delta E at least, for a reaction, right? When I talked about delta E in the previous video, I said right at the end of it that it's a state function. Which was another word for saying it's path independent. That means if I have the reactants and the products right, it doesn't matter by what process I imagine turning the reactants into the products. The change in energy for getting from reactants to products should always be the same. So we're going to make up an actually kind of ridiculous way to do a chemical reaction right now. Okay, it's ridiculous in that it would never happen this way, but it's convenient because it'll help us be able to calculate things. So imagine we do the reaction by taking all the reactant molecules, whatever's on the left-hand side of my equation, and just completely dismembering those molecules, breaking them up entirely into atoms. Okay, I'm going to break all the bonds that exist in there. So I just have an array of atoms. Okay, I'll still have the same number of atoms of each kind as were in my balanced equation. Then I'm going to take those atoms, stick them together to make new bonds to make the products. Okay, if my equation was balanced in the first place, I should still be able to use up all the atoms. They've just been rearranged into different things to be the products. Well, these different steps cost energy, meaning do I have to put energy in, or release energy, meaning I'll get energy back out. Well, they should be opposite in direction, right? And I said in the previous video at the very outset, I said making bonds always releases energy, right? That's why bonds form. That's why two atoms stick together. It's because doing that will lower their total energy. So when I make bonds, releasing energy, that will correspond with making bonds. Will it cost energy? That will correspond to breaking bonds. Okay, so in this case, I want to break the bonds in the reactants, and I want to make the bonds in the products. Energy going in, where it says cost energy, that term wants to be positive. Energy being released or coming out, that term wants to be negative. Okay, so that leads me to an equation that will tell me how to use these energies to calculate delta E. And it's a fairly simple equation, right? It says delta E for any reaction. We can estimate this by taking the sum of all the bond energies for all the molecules in the reactants minus the same sum, all the bond energies for all the molecules in the products, all right? Warning about this equation, as the next week or two go by, this equation is going to seem more and more backwards, okay? Because it's the sum for the reactants minus the sum for the products. We're going to meet up with several equations in the next few days, all of which will be things for the products minus things for the reactants, okay? The fact that this one goes the other way around is really a function of the fact that in those tables of bond energies, people always write the table with the numbers in there as positive numbers. If we put negative signs on all those numbers, then the products and reactants would switch in here, but that's not how it ever is. So it's just one that we have to kind of keep track of. The best way is just to ask yourself, like, which part is energy going in, which part is energy coming out? So I'm going to illustrate this by just doing a calculation. Note this will be our first numerical problem for quite a while. That generally makes people happy in this course when we get to this point and numbers come back into the problems and into the assignments. This equation is for the combustion of propane. Okay, propane is C3H8. The combustion of propane is what happens if I go out in my backyard and light up the gas grill. And that should tell me I'm going to find delta E for this reaction. I should be able to say that delta E for this reaction, it must have to be negative. It should be less than 0, right? I can tell that because it's a fire, right? It's propane on fire. It's a combustion reaction. We do combustion reactions when I turn on the gas grill because I want a source of heat, right? I want the molecules to be releasing energy, and I want that energy to show up to be used to cook my food. And so that says I'm going to get a negative delta E if I do the calculation correctly, all right? To use bond energies, I have to know what kinds of bonds I have and how many of each kind. So I'm going to sketch out real fast Lewis structures for the things involved. So C3H8 has 3 carbons, and then I just fill them all in with the hydrogens to get everybody up to 4 bonds, and that will be my 8 hydrogens. I should put the 3rd carbon in before I try and put the hydrogens on it, right? So in 1 mole up here of C3H8, I would have what? I would have, why am I writing a 5? I don't know. I would have 2 moles of CC bonds. I have 2 carbon-carbon single bonds, plus I have 8 carbon-hydrogen bonds in there. I'm going to interpret them as moles. We'll come back to that point in a moment when I do the calculation. Oxygen, O2, Lewis structure for that is a pretty simple one. I'm drawing all these by the method of A, having seen them recently in most cases, and B, just knowing what they look like. Obviously, it might take you a little bit more effort to draw the structures. That's not meant to say that you should know them just like I do. So in there, I've got an OO double bond, right? And if I have 5 oxygens on that side, that will mean I have 5 OO double bonds to break because I want to take my reactants entirely apart into atoms. Those are the reactants. Now I'm going to the product side, so I'll draw myself a little line there to remind me of that. CO2 we've drawn a couple times recently, and so we'll just write that one in like this. Each CO2 has, 2 carbon-oxygen double bonds, and I have 3 of them here, so I'll need 6 CO double bonds. I've got H2O. We've seen that one a lot recently as well. Looks like that. So each molecule would have 2 OH single bonds in it. I have 4 of them, so that means I'll have 4 times 2, or 8 OH bonds that I have to break. Okay. No, I have to make, sorry. Over here, I'm breaking. My little line to divide my products and reactants didn't really help. And over here, I'm making bonds, okay? That says, again, energy is going in to break the bonds from the reactants. Energy is coming out to form the bonds in the products. So let's now do the calculation. I'm going to start, and I'm just going to pull my two sides up here separately. So I'm going to say on the reactant side, just to summarize what we had there a minute ago, we had two CH bonds plus two CC bonds. I'm really just doing terribly at writing here, sorry. Plus 8 CH bonds. And then that's all the bonds I have. Oh no, I have my oxygens, right? So I have then 5 OO double bonds to deal with. I'm going to put in the bond energies from the table, and then I'll talk about units separately in a moment, okay? The carbon-carbon bond energy was 345. That was in kilojoules per mole. The CH bond energy is 415, also in kilojoules per mole. And here I have 493.6, where that extra decimal place digit there is just because that's measuring the real bond energy for O2, right? Where no matter how many O2 molecules I measure, they should all have the same bond energy. If I multiply that stuff out, my notes tell me that I get 6478. And now let's talk units. The things in parentheses are in kilojoules per mole. Right, so that's in a molar quantity. That means I'm going to think of doing, instead of 1 molecule of propane, think of doing 1 mole of propane. So in 1 mole of propane, I would have 2 moles of CC bonds. So I'm going to multiply moles times kilojoules per mole. That means I'm going to get kilojoules here for a unit. Okay, so it would cost me 6,478 kilojoules to take a mole of propane and 5 moles of oxygen and take them all apart into atoms. This is energy going in again. On the product side, I have what? I have 6 CO bonds and I have 8 OH bonds. And that says I'm going to get 6 times 800 for that carbon-oxygen bond energy, plus 8 times the OH bond energy, which is 460. Again, those are moles for the coefficients and kilojoules per mole for the energies. Multiply them, we get kilojoules. I get 80 kilojoules there, right? This is energy going in. That's positive. This is energy coming out. And that should be negative. That means when I put these together, I want to say delta E, right? And E is equal to, sorry about the third line, my pen is hesitating here, 6478 minus 8480. And that, when I subtract it, according to my notes, is equal to minus 2002. And that should be in kilojoules. Okay. A word about the units on these things. We're going to write things like delta E for a reaction with units that just say kilojoules, just energy units, okay? If you look in some other sources, if any of you remember like a textbook from maybe AP Chem class or something like that, you may have seen something that said kilojoules per mole for these quantities. We don't do that in our book because that 2,000 kilojoules that's down there, that says that's how much energy will be released if we do exactly what the equation says. So in this case, it is 2,002 kilojoules for 1 mole of propane, but it's 2,002 kilojoules for every 5 moles of oxygen, or for every 3 moles of CO2, or for every 4 moles of water that are in that reaction, right? Some books would call that 2,002 kilojoules, quote, per mole of reaction. We just chose not to use that phrase because I find that it confuses students more than it clarifies when I talk about moles of reaction, Okay, so hopefully I didn't just do that here. Again, the best way to think about those and make sure you're getting your signs right is two things. One, if possible, like here, because it was a combustion reaction, we kind of should know the answer has to be negative, right? So if I do that with the signs backwards, I'll get a positive answer, and I should realize that can't be right. A lot of reactions, you can't do that, right? But the reactant bonds, those are being broken. Those cost energy, so that's energy going in. Energy going in is always a positive quantity. Energy being released or coming out should always be a negative quantity.